So that we have discussed what we have here in terms of composite and non-composite beams, a concept. Now, since we have this composite beam or non-composite beam, we're going to have a metal deck, and the metal deck is going to be attached to the steel beam. In composite, the stud spacing, because this stud is not going to be just one stud, it's going to be many studs throughout the length of the beam. And the maximum spacing between two studs is going to be a foot, like 12 inches. In this case, the top flange is going to be completely braced from lateral movement, right and left. Once you put any loads, if there's no bracing to the top of the beam, this top flange now wants to go right or left. It depends on the loading.
Sir, what is the maximum spacing allowed between two studs?
Maximum spacing 12 inches usually. In construction, we make it from a stud to a stud throughout the length of the beam, which means perpendicular to the screen here, is going to be a foot, like 12 inches, right?
Okay.
So with this spacing here, there is no chance for this top flange here to deflect right or left. So in this case, the deck is going to be attached to the top of the beam. It's going to be bracing it. And this is going to be good because the buckling length of the beam here is going to be equal to, let's say, a foot. It's going to be very small. Now, what happens if there is no good connection between the metal deck or concrete deck and between the beam? It means here that the top of the beam is going to be rotating right and left. It's going to be moving right or left. And the strength of the beam is going to get reduced. It's not going to be as strong as when you have this connection between the metal deck and the steel beam, whether you have it as composite or non-composite. But just because this is going to here, the top of the beam is going to start to buckle either right or left, it's going to be a loss in the strength. And I'm sure that you guys studied this in the steel one, and you have seen graphs that shows with the buckling length of the beam, you're going to have some reduction in the flexure strength, not the shear strength. Okay. Let's say that you have a beam here, and there's no metal deck on the top, nothing at all on the top, which means no bracing. But you come here, you start to put some bracing points. How do you put this bracing points? By providing either a brace in the lateral direction, which means if I'm going to go back here, I'm talking about that you're going to see here a beam is going to be right and left, or a brace, like a steel brace that you're going to see there. This is what you call here bracing element, or this is going to be putting here a bracing point for the steel beam. Now let's look here at the maximum spacing between two brace points. As you see here, the maximum spacing between two brace points is going to be this L3. So now the buckling length of the beam, instead of being the total span L, it's going to become how much now, or what? It's going to be L3. So L3 here is going to be the buckling length of the beam. So instead of having the total buckling length of the beam to be the span, we're able to reduce it to L3. So in many cases, you start here to design unbraced top flange beam. All of a sudden, the strength is not good enough. So one of the options that you can do, that you're going to put here a bracing point, let's say at the mid span. And with that, you cut the buckling length into half. This provided that I don't have here a metal deck on the top, because the easy way, instead of adding here a structural member for bracing, is just attach the metal deck to the steel beam. So now we have two options. Some beams have metal deck, and in this case, it's going to be bracing the top flange of the beam. And it says here, buckling length is going to be almost equal to 0. If you have metal studs, like to the concrete, let's say it's going to be about 12 inches or a foot, which means design-wise, it's going to be equal to 0. I mean, 12 inches, it's not going to be affecting your design at all. But if there is no metal deck, and you have some issue with the strength of the beam, in this case, what you need to do is to put some bracing points. This bracing points is going to be bracing top of the flange, and it's going to be cutting the buckling length from the total span to the maximum distance between two bracing points, or two bracing elements. Like in this case, in this picture, it's going to be L3. Now, if the top flange is totally braced, like in this case. The flexure strength of the beam is going to be equal to, this is going to be phi min, the flexure strength, the capacity, is going to be equal to phi factor of 0.9 multiplied by yield strength multiplied by the Z factor. What is the Z factor? Z factor is going to be the section modulus, and you can read it or look it up from the steel section. So let me go up here, W sections. This is from the introduction. Slide set. Can be going here. Let's hope it's gonna be there. It's gonna be on the other side of the page. Do you guys have the steel manual handy? Anyone has it handy?
Yes, Professor.
Okay. Like in this value, for example, this Z, section modulus. So usually in the steel book, you're gonna see here 2 pages. They're gonna be against each other, next to each other. The left page is gonna include this, like in the W section. This is the section I have out of it. And the right side or the right page, you're gonna see lots of other information like moment of inertia, radius for gyration, and many information, including also section modulus. Section modulus, we have 2 of them. We have the elastic and the plastic one. The elastic is called, like in here, it's called S. This is the elastic section modulus. The plastic section modulus is going to be this Z, and usually this is more than this. When the entire section here is plasticized, as you guys have studied before, structural steel 1, look what happened. The value is much larger than the one for the elastic analysis. Look at these values compared to these values. So good thing we're going to be doing here plastic analysis when it comes to flexure strength, and we're going to be doing this Z factor about the x-axis. So back here to our flexure equation. If the buckling length is equal to 0, phi min equals to a phi factor of 0.9 multiplied by yield strength multiplied by the Z factor. Z factor again is going to be the plastic section modulus. Okay, good. How about if I have some length? What should I do? I'm going to say, okay, in this case, you need to go back here to some tables in the structural steel manual. And of course, there's lots of equations. And you're going to be including this L sub B, which in this case is going to be equals to L3, and put in the equation and get some reduction factor to the flexure strength. You guys have studied this in structural steel 1. In here, I'm going to be targeting the composite sections. So I'm not interested in repeating this section that you guys have covered already. When it comes to shear strength, there's no reduction because the buckling length of the beam. And the shear strength for the beam section is going to be equal to phi sub V for the shear times, usually, instead of using F sub Y, when it comes to shear, you use 6% of F sub Y. So this kind of standard. Once you see your shear strength, you usually have this reduction of 0.6 times Fy. So instead of using F sub Y, use 6% of it. How about the phi factor? Phi factor, we're going to be going through it. We're going to see how much is this phi factor. But usually, if you're going to be using this 6% of reduction, it's going to be equal to 1. It's not 0.9. 0.9 is going to be used for the flexure. Times CV, which is coefficient that we're going to be going through. We're going to see exactly what value do we use for it. But most likely, it's going to be equal to 1. So this is some good news. This is going to be simple. It's going to be 1, and this is going to be 1. About 8W, the web cross-section area. Now, where is the web? Someone's going to say, this is going to be the flange. And where's the web? Some people say the web starts from here to here. But look at this picture. Area of the web is going to be equal to the total depth of the beam. Now, when you talk here about total depth of the beam, you need to look it up in the steel manual, in the steel book, and you take it from here, like in our case. I'm talking here about W44 by 230. Depth is 42.9. Don't say now it's going to be 44. 44 is nominal depth, which means it's about 44 inches. As you see here, it goes from 44 to much lower value. So in this case, for W44 by 230, let's use this factor or this number, and let's not use this factor. This factor here or this number is going to be used for detailing and construction. This number is used for analysis and design. So the area of the web is going to be equal to the total depth multiplied by the web thickness. Again, where did you get the web thickness from? Again, from the steel table. Let me show you where do we have it here. This is going to be T-web. Now, in our case, T-web is going to be 0.71 square, it's going to be an inch. You do this number, the depth, times the web thickness in inches, you get this area of the web in square inches. So, okay, good. Now, let's see the factors that you're talking.
Sir, what did you say was the value of strength reduction factor?
I'm sorry, can you repeat again, please?
What will be the, okay, it's given.
All right. So in here, this is the two factors that I'd like to work with. It's going to be the strength reduction factor and the coefficient for the shear. As long as H over TW, what is H in this case? Which means D, the depth, is also here called H. This is now in the ACI, in the AIC for the code itself. Once this H divided by TW is going to be less than or equal to 2.24 square root of E divided by F sub Y. How much is E? I'm going to put here 29,000. K psi and F sub Y is going to be based on the steel. And in most cases, for W section, let's say it's going to be equals to 50. This means almost for all beams, phi sub V is going to be equal to 1 and C sub V is going to be equal to 1. As it says here, this applies to all grade 50. As long as this Fy is going to be equal to 50, this is going to apply to all sections. So this rule here is going to apply to all sections, except for the following. Phi sub V is going to be equal to 0.9 for only these sections. So as you see here, how many sections you have? You have 8 sections. That's it. Any other section, you're going to see here, phi sub V is going to be equal to 1 and C sub V is going to be equal to 1.0. They made it easier for us. Any questions?
So even for the 8 sections listed below, CV is still going to be 1, right?
Yeah.
Okay, thank you.
Sir, the formula given at the side, H over TW less than 2.24. So
Yeah.
this formula is, when this formula is applicable, then P sub V is equal to 1 and C sub V is equal to 0, right?
This is correct. And if you run it throughout all the W sections, you're going to see that it is true, that this correctness check applies. So you're good. Okay?
Yes.
All right. Now for the beam design, as I said, first you need to do strength design. So you need here to do a check on deflection and shear demand. Again, it's deflection and shear strength. So first the demand, we know the demand. We're going to have a load factor. We're going to find out the moment and shear that we need to design for. For the deflection design, here's Phi-man. As long as the top flange is going to be braced. If the top flange is unbraced, we need to figure out the unbraced length or the buckling length and use it in determining the reduced strength for deflection. For the shear, we're going to be using this equation. And with that, we're going to be done with the strength design. This is not the complete design of the beam. We have a strength design, and then we have serviceability checks. As it says here, serviceability check to be conducted, the total dead load deflection and live load deflection, according to the code. Now check on deflection. Now this for serviceability. The equation for uniformly distributed load says 5WL to the 4 divided by 384 ER. And then I added this factor here, 1728. And here's the reason. If you open any structural analysis book, you're not going to see this factor. The reason because if you like to use this equation, you got to be careful with units. So for example, if W is going to be kip per foot, let's say this L needs to be in feet, and this E needs to be in kip per square foot, And this I needs to be in foot to the 4. But reality is, usually this moment of inertia, we have it as an inch to the 4. And this E, we have it as a KSI. And this W is going to be kip per foot. And the span usually is going to be in feet. So we need to have some conversion factor. So if you like to use here the load as in kip per foot, and the span to be in feet, and E to be 29 KSI, and I to be in inches of 4, you need to have this factor here, which is 12 cubed. So if you say here 12 cubed, is going to be equal to 1728. So this equation here is good as long as you have all of these units used in this equation. If you like to use any other equation, let's say for a point load deflection. When you have a point load deflection, you have the span is going to be in feet, point load is going to be in kips, E is going to be inches of 4, and I is going to be inches of 4. You still need to use this exactly same factor, 1728. So, okay, good. All right, this is going to be deflection. Now, this deflection is going to be once we do it for the live load. So this W here can be once live load, and once it's going to be total load. So we don't do dead load deflection only. We do either live load deflection or total load. After you do deflection, this is going to be coming here to you in inches. Take the span here and divide it by the deflection. Okay, I'm going to take the span divided by deflection. It's going to get you here a factor. You'd like this factor to be as big as possible because when deflection is going to be very small, this factor is going to be big. Does this make sense? Yes?
Yes.
All right. So in this case, I'd like here this deflection to be small. And my deflection limit in terms of the span is going to be equal to, here is the live load allowable deflection. It's going to be equal to the span divided by 360. Now in this case, when you do the span, do it in inches. So if the span here, let's say, is going to be 30 feet, your allowable live load deflection is going to be 1 inch. How's that? 30 times 12 is going to be 360 divided by 360 is going to be an inch, which means live load deflection now is going to be 1 inch. Total deflection, if the span equals 30 feet, is going to be 1.5 inch. Does this make sense? Yes? So what?
Professor?
Yes, go ahead.
Sorry, how did they get those values to divide the span by 360 and 240? You know why?
360 and 240, this from the code.
Oh,
This
okay.
is the California Building Code, International Building Code.
But you don't know why they came up with that?
This is based on analysis for them, what's going to be acceptable to people walking below. This is
Okay.
And what they are saying that this limit here is good for steel beams, concrete beams, wood beams, which means for any beams. You can use this limits for the live load deflection and total deflection.
All right, thank you.
So as I'm saying here, for sake of discussion, I'm throwing a span of 30 feet. So in this case, live load deflection is going to be equal to 1 inch, and total load deflection is going to be 1.5 inch for this beam. Whether you do it out of steel, concrete, wood, whatever, this is going to be the limits. So what you need to do for the beam that you're going to pick and choose in your design, you have the moment of inertia for it, right? You know it's going to be steel, so E is 29,000 KSI. You have the load applied to it. So figure out deflection due to live load compared to this number. Do total load deflection due to dead load on live load and compare it with this number here, which means 1 inch. If your deflection, actual deflection, is going to be lower than the limit, you're good. If not, your beam design is not good, code-wise. So you have an issue here with serviceability, not with the strength. In many cases, you do a check on a beam, and this check number 1 and 2, which means the flexure and the shear, they're good, but deflection is bad. It's not working. So you need to pump up the size of the beam. You need to pick a larger beam.
So what is the main difference between maximum deflection live load allowable and maximum deflection total load allowable?
All right, this is a good question. Life load deflection is going to be deflection due to the stuff that you put in there, like occupancy load. In an office, it's going to be the weight of the people, the weight of the furniture, and this kind of things. So we call this life load deflection, right? So you need to figure out how much is a life load, as in kip per foot, and plug it in this equation here and figure out deflection due to the additional load besides the dead load. And with that,
So over here, L is load or span?
what?
In this equation, L is load or span? L over 360 and L over
This one
240.
here,
Yes, sir.
this is a limit, and this limit is based on the span of the beam.
I mean, what does L denotes over here? Span or load?
L is the length, right?
L is the length, it's the span. Span is the length. The span of a beam in the structures and in statics is going to be the distance from a support to a support. The span of this beam is the distance from this point to that point.
Okay.
And in structural analysis, if you like to do deflection, you're going to be using this equation. Have you seen this before in the statics and mechanics of materials or not? If not, let me know, because in this case, we need to discuss deflection and what happened. What does it mean by deflection? How do you calculate that?
I don't think I've seen
I
it.
will assume that you guys know it, unless someone is going to say, no, we don't know it. So in this case,
I don't think
go
so.
through.
I don't think I've seen it.
You have not seen, have you taken the statics?
Yes, sir, I did.
Say it again.
Yes, sir, I did.
Okay. And have you taken mechanics of materials? No?
I think so.
Okay. This is like before, usually before you take a design course, you need to take statics course, and then at least structural analysis 1 after statics. And also you need to take mechanics of materials, because when it comes to stresses and strains, when it comes to deflection, this is going to be like the basic knowledge that you need to have. But let me explain to you. You understand the meaning of deflection? I mean,
Yes, sir.
Okay, deflection means sagging, like when the beam comes down.
Yes.
So this deflection is going to be like the maximum deflection at the middle span of the beam, right? This how much is going to be going down due to these applied loads. And it is measured here in inches. W usually is used for the uniform load applied on the beam, as in kip per foot, like uniform load, right? L usually refers to the span. You see the span, which means the distance from a support to a support. And it is given here to be in feet. E is this modulus of elasticity, and is going to be fixed for all type of steels. We use 29,000 KSI. You guys are aware of this, right?
Yes.
Yes.
Good, all right. And I is going to be the moment of inertia that you take it from the table. I can put here this table back again for you, so that you see the moment of inertia listed here. So usually you read it off the table. I'm gonna put it here in a second from them, like in here. Here's moment of inertia for that section. So this moment of inertia about the x-axis, this is what you need to use in your equation. So let's say that you pick a beam section, or like of any sort of any section, and this moment of inertia, you just look it up in the table. You don't need to calculate out yourself. All what you need, just look it up and use it in this analysis. And with that, you're gonna have deflection due to this applied load. Now, if you use in your equation, if you like to use in your equation total load, which means dead load plus life load, we call this, in this case, if you put here total load, deflection resulted here is going to be called deflection due to what? Total load. If you put only life load, deflection here that we're going to be looking at or figuring out is going to be called life load deflection. It's going to be the actual deflection due to this applied load on that beam that you picked and choose. Now, you need to compare this life load deflection with the limit, and dead load deflection with and life load deflection all together. You compare it with this total load allowable deflection. And certainly you don't want this demand deflection to exceed the limit. You'd like to be within the limit. If this makes sense to you guys?
Yes.
Yes.
Do I have any questions on that, or we're good?
Is there a scenario where we use the moment of inertia by the y-axis?
This is a scenario when you use the moment of inertia, yes, for the beam. Yes, about the x-axis. Because usually, the way that you're going to be looking at the beam, this beam is going to be looked at this. Where is the x-axis? X-axis is right here, right? And look at the beam. Standard beam, how it's going to look like. The beam is used like this. This is going to be the x-axis. So the moment of inertia I need to look at is going to be the x moment of inertia about its centroid. All right. All right, we're going to see some examples. Usually numbers is going to make it much easier. This numerical example is very useful. So it says here top flange braced beam. So this is given to me. The top flange is braced. This is some good news. I don't have any buckling and I don't have any composite action. Dead load is given at 80 pounds per square foot. Life load is given as 50 pounds per square foot. Now, can I do any reduction on this life load? Just a question here. Should I reduce it like what I have done in the past, in the previous slide set? I'm gonna say no. Why? Because reduction is gonna happen when you know the occupancy. If you know that this is an office occupancy for residential, you can do reduction for life load. If the life load is given to you as a number, you do not reduce it, just use it as is. The steel used is going to be ASTM A992 grade 50. Now I know the F sub Y is going to be equal to 50 KSI. Tributary width for the beam is 10 feet. Anyone has a question on the tributary width definition? Yes? No?
We're all good.
All right. Here is the tributary width. Tributary width is going to be the distance from here to there. So in this case, this side is equal to 10 feet in this example. The span is 30 feet. What is the span? The span is going to be the beam length. The distance from one support to one support in feet is going to be 30 feet. It says here, determine the most economic. What does it mean by most economic? It means a lighter beam. Now, when you look at the beams, let's say that you see W16 by 31, W16 by 36. Now, which one is lighter? The one that has a smaller number as a weight, like 31, for example, or 26 or 36. Or W18 by, we call this just W18 by, there's no weight because I'd like to use one of this W16 bys. I don't know exactly which one. So this is gonna be my choice. It's gonna be my design. So in a case like this, I'm gonna have two checks. One is gonna be for the flexure for the moment. Second one is gonna be for the shear. And then serviceability check, which means check on deflection for life load and total load deflection. So let's go through this in details. Dead load is going to be equal to this uniform load, the 80, multiplied by the tributary width, the 10 feet. So in this case, this 80 PSF means 0.08 KSF. How can I do here the conversion? You just divide this by 1,000 because of 1 kip equivalent to 1,000 pounds. So this is going to be here 0.8 kip per linear foot. KLF means kip per linear foot. And the life load, I'm going to be taking this 50 PSF again times 10 feet for the tributary width. It's going to get me here 0.5 kip per linear foot. I'm doing here LR of D, which means I need to use factor loads like 1.4, 1.2, 1.6, this kind of things. But also I will need the total service load, which means dead load plus life load when I do deflection check. So this number here is need for deflection analysis. So when you do here serviceability check, you don't use any factors. I'm gonna take you back here one slide. When you do here flexure and shear check, you're going to be using ultimate load, meaning that you're going to have the load factors, LR of D. When you do the service check, use the loads as they happen. There's no factors. Just add dead load to life load in your analysis. This is the reason that I'd like to add both of these two for deflection analysis, for serviceability analysis. When it comes to the ultimate, I need now to figure out the ultimate load. So I need to try 1.4 times dead load. See, here's the dead load, 1.4 factor. Compare it with 1.2 dead plus 1.6 live. Now, which number controls? Compare this to, this is controlling here my design. I see a question coming.
Professor, I just want to ask, are these the only two equations that we consider for LRFD design?
This is correct, as long as you have only dead load and life load. So in this problem here, it says dead load, it says life load, and this will be the only factor that you need to consider in this exam. Okay. But let's say in real practice, I'm going to take you back here. Let's say that I have soil pressure. Where is soil pressure? It's going to be H. And I have dead load. There is no life load. So in this case, I'm going to be using this. I'm going to be using here 1.6 times H. Let's say that I have seismic force. Like I'm designed for seismic earthquake forces. It's going to be this E. So in this case, I'm going to have dead load, life load. So any equation here that shows dead load and life load, I need, and earthquake, I need to consider them. So I'm going to say this gun, yeah, 1.4 dead. I'd like to consider this. This could be there. This could be there. This one also includes E. This one, no. This one, yes. So it depends on the given loads. So in this course here, for the first section, I'm going to be working only with dead load and life load. Once we go to seismic moment frame and eccentric brace frame, it's going to be all about seismic forces. And in this case, this is going to be used. Okay?
Sounds good. Thank you.
All right. Okay. So again, I'm back here to the load equation, load factors. So I find out that 1.2 dead plus 1.6 live is going to give me here a bigger number than 1.12. And this is going to be my load to figure out the shear demand and moment demand. Now, this is going to be simply supported beam. The span is 30 feet. You have a load of 1.76. How much is the moment? It's going to be the simple equation. W squared divided by 8. How about the shear? Shear is going to be the same as a reaction. WL over 2. So we tried this, and here's the moment demand, and here is the shear demand. Any questions on the shear demand and moment demand? This slide is good?
All good.
All right. Very good. Now, flexure design. I decided here to use W16 by 31. Okay, good. This is going to be my choice. Looked up the ZX, which means the section, plastic modulus. And turns to be 54 inch cubed. It's all right. Let me try here to find phi man. Be careful about this trick here. You're going to be doing here phi factor, 0.9. F sub y is going to be 50 KSI, kip per square inch, multiplied by inch cubed. So the units I use here is going to be kip and inch, but you'd like to see the moment in kip and foot. So when you have moment in kip and inch, you need to divide here by 12 to get it in kip foot. Why do I need to be in kip foot? Because the demand, if I'm going to go here back one slide, was given here or was calculated out based on kip foot. So I'd like to keep all the factors, all the moment to be in kip foot, and the shear is going to be in kips. That's okay. Here is the capacity. The demand was equal to 198, previous slide, 198. So we're good. This beam section is great when it comes to flexure. Good choice.
Professor?
Yes.
Oh, sorry. For you, did you choose 1631 because that's the first one without a note on in the book?
What do you mean?
You know how when you go to the shapes and you pick, you look at the ones available for 16,
yes,
which is not that much, right? And The first one for 16.
By 26.
26 and then 31. I'm assuming you picked 31 because it doesn't have that extra note on the
Well,
shape.
I'll tell you the reason. No, I can tell you the reason. If you try 16 by 26, it's not going to work.
Okay.
So I know this ahead before I put the example, right? So I know it's not going to work strength-wise. So I just picked the ones going to start to work.
Okay, thank you.
This is my reason. So in your case, let's say that you're doing this for homework or exam. So definitely like to start with 16 by 26. But if you try it in your calculator and the numbers are not good, don't write it down. You can do this quick in your calculator, right? If you're not satisfying here the first strength point, then you just move forward. So according to this number here, this is going to be very good design. I mean, these two numbers are very close from each other, which means the design is good. I don't have lots of room, like difference between the strength and between the demand. This beam is good. I'd like also to take the shear. When you check the shear here, web thickness is 275. Depth, 15.9 inch. Area of the web is going to be 15.9 times 0.275. For this beam section here, your phi factor is going to be equal to 1, and C sub W is going to be also equal to 1. So I didn't put it here even in the equation. And with that, the strength here is 131.18 kips. Your demand, if I'm going to go here back one slide, 26.4. Is very healthy. So this beam section.
Sir, what if both the values are almost equal?
What type of what?
What if both the values are almost equal? Like for phi m sub n, if it was 199 and 199 was our answer, then should we say it's okay, or should we get another section?
Can you please repeat this again? I'm sorry.
Sir, if our answer for PMN is 199, for example, and the demand is 198, so should we say that this is okay, or should we get a better section?
If this is 198, if the demand is 198 and the strength is exactly 198, you're good.
Okay.
If they're exactly the same as each, I mean, if they are identical numbers, I'm okay with this. Your design is good.
Okay.
All right, nothing is wrong with your design code-wise. But
and
yes,
if we increase it, then
if you increase the capacity, like in this case,
yes, sir.
yeah, this preferred that you need to leave some room. You don't want
Okay.
your design to be tight, just in case if you have done a little bit of approximation, rounding up your numbers or rounding them down, or I mean, if they are not exact, if you are concerned about that you may have a difference, let's say about 1 foot, so you'd better go a little bit above this number.
Okay.
Just in case. But if the demand is exactly equal to the capacity, you're good. There's nothing wrong with this.
Okay.
So strength-wise, this beam is good. This section is very good. I mean, satisfies the flexure capacity and the shear strength. I mean, they're good. Nothing is wrong with it. But now let's do a check on the serviceability deflection check. Now, in serviceability check, I'm going to take you here back one slide. I cannot use this ultimate load when I do deflection. I'm going to be using the service loads because deflection is going to be due to life load and total load. I'm going to take you also back one more slide just to remind you here. I have the limits given by the code that says here life load deflection and total deflection. Life load means only life load. There is no here load factors at all. Okay. So I'm going to do here check on deflection. I'm not going to start here with W16 by 31 because it is going to fail. How do I know that? Because I tried the number before I put it here for you. To save the time, I found out that W16 by 31 is not good. And the best choice here is to jump W18 by 35. Someone's going to say, let's look here at the steel table. The steel table includes W16 by 31. And what's the next size in W16 by? Can someone let me know? Read it out for us. What's next to W16 by 31?
16 by 57, or I mean the most efficient.
The one, so you have 16 by 31.
You have
or
also 16 by 36 if you want to go up by number.
36. Okay. So 36 is going to be the next one. The weight of it is going to be 36 pounds per linear foot. But look at this size in 18, W18 by 35. So would you rather go to W16 by 36 or 18 by 35?
18 by 35.
Go 18 by 35. The good thing, if you'd like to compare here, I want you also to compare between W18 by 35 and W16 by 36. Which one has higher moment of inertia? You know, when the depth goes larger, moment of inertia is going to be jumping up. So actually, W18 by 35 is stronger than W16 by 36. Even though the W13 by 36 is heavier, it has more material. But because of depth, you're going to be gaining here lots of moment of inertia. Now you can compare the two numbers for moment of inertia about the x-axis, and then you can let me know whenever you find it.
The W18 by 35 has a moment of inertia of 510 inches to the fourth, and 16 by 36 has a moment of inertia of 448.
Big difference here. Yeah, good at like 10%. So definitely I'm gonna be going with this. It's lighter, which means it's gonna be cheaper, and also it has bigger moment of inertia, the 510. Let me try here the deflection equation. Deflection equation says 5WL to the 4. What is W? The load. Which load? Live load or total load? So for now, I'm just gonna leave it as W. L is gonna be the span. The span means the beam length from a support to a support. 384 is a constant. E, 29,000 KSI. I is gonna be moment of inertia, which means for this beam is gonna be the 510. Now let me look at the numbers. 5, 30 to the 4, the span, 384, 29,000. This is the E, moment of inertia is gonna be 510. How about the W? Which weight did you use? I didn't use anything yet, as you see. So deflection in inches is going to be equal to 1.23 times W as in kip per foot. The reason that I put it this way, just to make it easier for me if I'd like to find out total deflection or live load deflection. So I'm going to say total deflection equals, use this equation, 1.3 times W total. Live load deflection equals 1.3 times W of live load. Try both of these two. For this deflection of total dead load or total load, excuse me, which means dead load plus live load, I have it as 1.6 inches for this beam section. For live load deflection, it's going to be equal to 0.615. So where's here total load? 1.3. Where's live load? 0.5. Where to get this from? I'm going to go back here one step. Here is 0.8 for dead load, 0.5 for live load, 1.3. I'm doing here check on two loads, live load deflection, the 0.5, and total, which means the 1.3. I don't do it only for the dead load. You don't do that. You do it only for the live load, and then you do it for the total load, the 0.5 and the 1.3. Now let's see here the limit. What is allowed by code when it comes to total deflection? As we say, this is going to be the span divided by 240. Now I want you guys to try quick. The span is going to be 30 feet times 12, divide this by 240. Let me know if this 1.5 inch is correct. Is it really
correct, Professor?
Yeah. Okay. Is this good? Now, actual deflection is going to be 1.6. Limit or allowed deflection for total load is going to be only 1.5 inch. So this is not good. I cannot use this. This beam section is not good enough. How about the live load deflection? Well, live load deflection, the span 30 feet times 12 divided by 3.6 is going to be an inch. Your live load deflection is 0.6 inches. So this is less than that, which means it's okay. So live load deflection works. Total deflection is not good. So what should I do? I'm going to go here to the following section. Should I go to W16 by 36? The next heavier section? You say, no, this is not a good idea because actually your moment of inertia is going to drop down. So I'm going to keep it as W18 and jump to W18 by 40. What happened W18 by 40? Moment of inertia is jumping. Now it becomes 612. Take this number
Professor?
again.
I'm sorry to interrupt, but how did we determine the moment of inertia capacity that we need?
This moment of inertia, all what I did in the W18 by 35, I picked the next section, which is slightly heavier.
I understand that, but why are we afraid to drop our I value, the moment of inertia value?
Why do what?
Why are we afraid if the moment of inertia value drops? Like, why do we need it above 510?
Okay, let's look at the equation here. Let's look at the equation and see if it's gonna drop, what's gonna happen to the deflection. If you reduce moment of inertia, what happened here to the deflection? Is it gonna be going up or down?
It's gonna go up.
So is this something good? We have a problem already with this moment of inertia. With the 510, it's not working.
Okay, yeah, I understand now.
Okay, so
Thank you.
to solve no problem. To solve this problem here, to solve this issue, I need to increase this moment of inertia. Why? Because I'd like to cut down total deflection. Otherwise, if I'm going to be going here with lower moment of inertia, this number is 1.6. Let's say it's going to be 2 inches. I'm going to say this is not good. You're moving here in the wrong direction. You'd like to increase moment of inertia. So when you increase it, what's going to happen to deflection? Deflection is going to drop down to be within this 1.5 inch maximum deflection. So what I did, I looked at the steel table. You have W18 by 35. Next size, next heavier size in W18 by is going to be W18 by 40. So I'm going to go, let me go here with this one. Looked up the moment of inertia about the x-axis. That was 612. So, okay, now what should I do next? Back check deflection. Someone's going to say, should I back check deflection due to total load and life load? I can say no. It is enough to do the total load. Why? Because life load is okay with this 510 inches of 4 moment of inertia. So I know it's going to work here with 510. So if you increase to 612, I don't really need to back check this. It's already good with a smaller moment of inertia. But I need to back check total deflection. So I'm going to say now total deflection. I'm going to be taking this equation, plug it in there, the 612 instead of the 510, and put the 1.3 for total, and here is the total deflection. It's going to be 1.33. Now this becomes less than 1.5, then this beam design is good, W18 by 40. Now I may have here some questions. Do I need to go back and do a check on the trends? You can say, well, you can just look at the Z factor. This Z factor for W16 by 31 is 54. Can someone here look this up for me and tell me how much is the Z factor for W18 by 40?
$78.4, Professor.
78 compared to his 54, much larger. So I have no problem. How about the depth? I'm gonna say, no way. I mean, the depth here is 15.9. How about the depth here? It's gonna be 18 inches. How about the whip thickness? Here I have 275. How about for W18 by 40? How much is this whip thickness? Do I have anyone else besides Michael to answer?
18 by 40, the web thickness is 0.315.
0.3. 0.3 times about 18 inch, so it's gonna be much larger. So I'm good with the shear and the flexure as is. So once you increase here the depth and you increase the weight, I'm sure that the strength is gonna be working fine by inspection, if this makes sense to you guys. We're good?
Yes, all good.
All right, questions?
How did you get the 1728 that you used in the deflection?
1728, I'm sorry, which 1728?
The next slide.
Here?
Yeah, like a second line.
Here?
Yeah.
Very good question, all right. And all right, no problem. And any other questions besides the 1728?
Professor, wouldn't it be more efficient to just choose the W shapes or that are kind of standing out? The W18 by 71, the 18 by 46, aren't those the most efficient versions of all the ones below it? with the highest inertia or the I value?
Yeah, you may find some of these, but my question to you, are you talking about W16 by 36 or W18 by what?
They're just the shapes and everything that actually are highlighted, essentially. They're the ones that are standing out in the steel manual.
Okay, this highlighting, it depends on the weight. And usually the steel manual prefers certain sections that you want you to use based on the Z factor. So actually it's gonna be sorted based on the Z factor. It is not based on deflection.
Okay, thank you.
No problem. That does make sense? My answer is make sense or not really, or not very clear?
No, it makes sense. I was just remembering in my past steel class that they mentioned, you know, if you want to go quickly to find maybe the closest answer, go to those, and then you can kind of reduce from there if you want to find the most efficient.
Yeah, this is correct, especially when it comes to the Z value, but it is incorrect when it comes to deflection analysis.
Okay.
Because deflection here is going to be based on the span and the load, but when it comes to the Z factor, it's going to be based only on the moment value. So let's say that you play here with the load and the span, and all of a sudden you make the span very large. Now deflection is going to be a lot, and you may keep the moment the same in the same section, right? So,
Okay.
so this applies only to the Z factor. So
Perfect. Okay.
No, thank you. Back to this question about the 1728. Now I need some help here with someone to try 12 times 12 times 12. How much is that?
1728.
Oh, this number, which means it's like 12 cubed.
Yes.
So let me go back here and look at this equation. What's happening there?
We are converting the span from feet to inches.
Absolutely, this is correct. Now, when you look at this equation, W is going to be kip per foot. And the span is going to be in feet. So here I have kips and feet, because it's going to be here kip per foot, and this is going to be in foot. So on the top here, I have kip and feet. On the bottom, I have kip and inches. And at the end, I'd like to see this deflection is in inches. So I need to get rid of the feet. How do you get rid of the feet? You convert the feet into inches. How do you do this? You multiply by 12. So this here kip per foot, and this here foot to the 4. So you have your kip per foot, and here is going to be foot to the 4. You end up with foot to the 3. You'd like to convert it, so you multiply by 12 to the 3, which is 1728. So the answer to this 1728 is going to be a conversion factor for foot to the 3 into inches. So at the end, my answer is going to be in inches. Did I answer your question?
Yeah, it makes sense. Yeah, thank you.
Right. One more example. It says here that de-install the beam of the previous example. You know it needs to be W18 by 40. Strength-wise, W16 by 31 was okay. There's nothing wrong with it. The problem was the deflection, the serviceability, right? So in this example here, it's true that W16 by 31 is strong enough, but doesn't perform that well. It's get deflect a lot. You know, once you see lots of deflection and you're inside the room, right below this beam, you're going to be kind of scared. You're going to feel that this beam is falling down. It's not falling down, it's strong enough, but just deflection is excessive that you cannot accept code-wise. So a mistake has happened. What they did here, they installed the beam as W16 by 31. Now they installed it already, which means all the bolts are there and it's in place. And they say, look for a fix. You realize this, you're at the site, and you find out that they didn't do the right thing. Now you need to fix it. An easy fix is to attach a plate below the steel beam to weld it to it, like in here. So you know strength-wise that this beam is good because you have the analysis. You start the analysis from day one and you know exactly what happened. You know that this beam size is good for the strength. You understand that you have just an issue for the moment of inertia. Look at the previous moment of inertia that you would like to see. It's going to be 612 or somewhere between 612 and 510 to make it work deflection-wise. So a good way of doing this is just to add a plate, and then you weld it here from the flange to the plate and from the flange to the plate. So this plate here is going to be increasing the moment of inertia. And hopefully it's going to be enough to make the deflection work. It says here, check the validity of this fix. So I need to back check this and be sure that, yeah, it's going to be working fine and nothing's wrong with it. Okay. Here is a steel beam and here's the plate. I'm gonna do my table. I have the beam and the plate, like section 1 and section 2. Cross-section area of the steel beam as W16 by 31 is gonna be 912. The plate is gonna be 1/2 inch by 6 inch. Forget about this 3/4 by 8. I'm not gonna be using this in my example. Why? Because my example says use only 1/2 inch by 6 inch. Okay. Cross-section area of this plate is gonna be 3 square inches. What is this Y? Now we're taking this, we're gonna have here like an X on the top of the beam. And for that, I need to figure out this Y1 and this Y2. Y1, this is from the top axis to the centroid of the W16 by 31 only. And Y2 distance from the top of the beam to the center of the plate. There's going to be some geometrical properties that you can work it out easily. Here is Y1 and this is going to be Y2. Y1 is going to be equal to 1/2 of this. Y2 is going to be equal to the depth of the beam plus 1/2 of the plate thickness. Now take the moment of this area about the top of the beam, A times Y. Multiply this by this, this by this, add them to each other, and A, just add the total area, divide this, divide by the total cross-section area. And with that, you're gonna get the new location of the centroid for the combined section. I know that you guys, you have taken this in statics and mechanics of materials before, but this is gonna be a very good example if you like to refresh your memory about it. Here's gonna be Y star, 9.98. So it is shifted down from the centroid of the original steel beam. How did you hear the moment of inertia for the combined section? You have the moment of inertia for each section separate. So the top beam, W16 by 31, moment of inertia from the table is gonna be 375. Moment of inertia of the plate about the x-axis is gonna be equal to 6 times 0.5 cubed divided by 12. It's gonna be very small, so I did not include it here. It's gonna be extremely small, can be just ignored. Y bar is gonna be the distance here from the new centroid, which means this location here, to the original centroid of each one of these sections. So this Y bar 1 and Y bar 2, you should be able to figure it out. Just like geometrical properties, you can run the number there. And then you do AY squared. Where is Y? This is gonna be Y bar times AY squared. Total moment of inertia is gonna be equal to this column plus this column. You add all of these values to all of these values. Here's moment of inertia, 375 plus this value, very small, just was ignored, plus 37, which is this number here, plus 114, which is this number here. Now I have 526.79 inch to the 4. Now this is gonna be the moment of inertia of the combined section. Now what do you do with it? You do again the total load deflection. Here's the total load deflection. It turned to be 1.55. It's still not good. So I evaluated this analysis, this solution. It turned to be that just adding a plate of 1/2 inch by 6 inches, it's not good. Any questions?
Professor, just wondering, this is not good code-wise, but because of all the safety factors that are thrown in, this beam would still hold the loads, right?
Yeah, but it's going to deflect a little bit more.
Okay, thank you.
So someone's gonna look at this, gonna say, what does it mean by 0.05 inch? It is nothing, right? You're not gonna see it, your eye is not gonna catch this. So in reality, if you see a case like this, what would you do? Just call it 1.5 inch. Right? Because 0.05 inches, you're gonna say maybe just some of the numbers. If I just gonna be working with some of these numbers, I'm gonna be going very exact, maybe it's gonna work. Besides, difference in deflection is gonna be very small. I may just say it's gonna be okay. But if you are doing an actual analysis, submitted, let's say for check, or you are doing a homework, you cannot say that this is okay. You need to make it work.
Because it will make the structure weak, so it's not okay, right?
Yeah, because the deflection that you have in there due to total load is going to be more than the allowed deflection. So the beam is strong enough. It can take the load, but it's going to deflect a little bit more than allowed by code. Any questions?
Professor, how did you get the 510?
All right, very good question. Let's go back here. Let's look at this equation here. This deflection equation that went up with, that says here 1.6 inches. That was based on a moment of inertia of 510. So let's say we made this to be 1020. I just double out the moment of inertia. How much deflection would you get? If I may ask you here.
Can you repeat that again, please?
If I double the moment of inertia and make it 1020, what happens to this deflection? Is going to be going up or going down? How much deflection would I have?
It goes down, it'd be 0.8, right?
Yeah, it's going to be 1/2. Why? Because you doubled this. So for deflection of 1.6, I have a moment of inertia of 510. When I have deflection of 1.6, I have moment of inertia of 510. So what happened when the moment of inertia goes up to 526? Can you find out now the new deflection? So you can just do it in this equation here. It's like by ratio.
So basically you multiplied it by 510 to remove the previous moment of inertia 510, and you divided it by 526.79 as the new moment of inertia, right?
This is correct. So the 526 is going to be the new moment of inertia. And here question was about where's the 510 coming from? So what I'm saying, the 510 is coming from the previous moment of inertia, calculated for deflection of 1.6 inches. So if you go back here to this equation, you're going to say, okay, let me take this. This is going to be equal to 1.6, right? And this is going to be in the denominator, right? So if you take 1.6 times 510, divide this by 528, it's going to get you the new deflection. If you feel that this is kind of confusing to you, just try the entire equation again. It should be fine.
Okay, thank you.
All right, thank you. Any questions before you guys leave? If you are good, please sign out in the chat room and you should be good. I see here Krambir. I've seen you joining us. Are you there?
Yes, Professor, I'm here.
All right. Very good. I have everybody here. All right, you guys have a good night.
Thank you, Professor. Have a good evening.
You
Good
too.
night, Professor.
See you Wednesday.
Good night, Professor.
Do we have Monday lecture? Just one?
No.
Okay, all right, good. So I'm gonna see Wednesday.
Sir, we won't have a lecture on Monday.
What's that?
On Monday, will we have a lecture or not?
Wednesday, yes. And Monday, no.
No, Monday.
No,
Okay.
we don't.
And
Okay.
Professor, when and where can we find the videos recording?
I'll post it. Okay, I'll post it. But also one thing that I want you guys to know about, I don't know if you have seen this already or not. Did you see this link?
Yeah.
Okay, you can download this version here, version 16 from here if you want to. And this is already on the canvas.
Okay, Professor. Good night.
Good night.
Thank you.
Professor,
Yes.